Hello everyone. Let us start with the importance of order of events in organic synthesis. So in retrosynthetic analysis, we need to follow a definite order in a particular synthesis. So when I see a definite order, that means a particular reaction has to be carried out first, followed by the second reaction. Let us consider this detergent. Now this is a detergent which is called a sulfonic acid detergent. Now in this particular target molecule, I want a sulfonic group, I want a long chain alkyl group, as well as I have to see that a sodium salt gets synthesized. So this is going to follow with a certain step of reaction. Now these are the events which are followed for the feasibility of the reaction. That means easy carrying out the process. The first one is alkyl, the alkyl group is electron donating and hence it will always allow easy sulfonation. But already if I have introduced a sulfonic acid, then it would be very difficult because sulfonic acid itself is a meta-directing group. So avoiding all this, how we can synthesize this detergent? Benzene in the presence of an alkene system with Friedel-Crafts alkylation, it will undergo Friedel-Crafts alkylation to give me a long chain substitution, which in the presence of H2SO4, it is going to give me a sulfonation reaction at the para position because long chain alkyl group is ortho para directing. Now this ortho group, it cannot go because of this bulkier system over there. So the only option that will remain is the para position, that is the sulfonic acid enters the para position, which in the presence of NaOH, H is abstracted, that is proton is abstracted, and I will be getting its sulfonic acid sodium salt. Now as we can see that first I followed a Friedel-Crafts alkylation, then I followed a sulfonation reaction. I didn't choose first sulfonic acid as the starting material. Instead what I did is first I did a Friedel-Crafts alkylation, then I followed this feasibility of sulfonation. Now these are certain of the events that I need to follow in my organic synthesis. Definitely there will be certain guidelines for this system. In this, the first guideline is disconnecting all the groups in turn to see if the reverse reaction would give the right orientation. Now let us come to an example of Oris odor ketone. That is, this is my target material. Now it has got two functional groups. First, what we have to do is we have to try to disconnect both the functional groups associated with it. Now what I will do in position number A, I will first disconnect the alkyl group and I will keep the carbonyl carbon intact. This is one direction I shall follow. The other direction is I will cleave out the carbonyl carbon group and I will keep the alkyl group with a leaving group which is attached to the carbonyl carbon. Now for example, if I choose a system where I have disconnected the alkyl group, now that will be my wrong orientation. And this is my right orientation where my carbonyl carbon group I have disconnected, because if already there is a presence of a carbonyl carbon, my entering group will go to the meta position. It will never go to a para position. So the choice would be the second choice, and hence the second choice would be taken as the right orientation, whereas the first choice will go as a wrong orientation. Now its synthesis we can see. I'll take up a benzene, I'll add an alkyl bromide in the presence of AlCl3 with a Friedel-Crafts alkylation. I can say that the long chain alkyl groups gets introduced at one of the position. Then when it reacts with acetyl chloride in the presence of AlCl3, there is an acylation to get me my target molecule, which is Oris odor ketone. So here we see that first we are going to do a orientation of the system. Whichever is the right orientation I am going to choose, and then I am going to do the final synthesis. Now, the second guideline is, if there is a choice, disconnect first the most electron withdrawing group because it is deactivating and it may be difficult to introduce any other substituents in its presence. Now, for example, these two beta-dinitrobenzene system, they both are electron withdrawing. What is the meaning of electron withdrawing? That the charge, that is the system, it is completely deactivating. So, further introduction of any other group becomes very difficult. So, what we will be doing is, first we have to try to disconnect the most electron deactivating system or the withdrawing group. By CN nitration, I will be doing a disconnection of these nitro groups. The other groups shall remain. Further, when I have Already removed those nitro group. Now there is a long chain, now there is an alkyl group and there is a methoxy system. With the Friedel-Crafts alkylation, I can introduce this long chain alkyl group. So I can remove this long chain alkyl group also. Now my starting material could be a methoxy system with the presence of tertiary butyl chloride. Now we can see here that in my starting material there is also a presence of methoxy system which can be introduced as an OH. So what we can do over here is, when there is a presence of this OH, methoxy group can be added easily by adding dimethyl sulfate system. So what we'll be doing is, we will be now again disconnecting this methoxy system, we'll be removing OMe, so that I'll be getting a metacresol system. Now this metacresol system, when it reacts with dimethyl sulfate system, it is going to give me a methyl ether. So following the synthesis would be something like this. Metacresol, it will react with dimethyl sulfate in the presence of a base. Now H is abstracted, so methoxy compound gets introduced. In the presence of tertiary butyl chloride, in the presence of AlCl3, that is Friedel-Crafts alkylation once again, there is an addition of this long chain alkyl group, that is a branched alkyl system, ortho with respect to the methoxy system, because methoxy is orthopara directing. Further, upon doing a nitration, that is HNO3, there will be an introduction of 2-dinitro system. So in this way I can get my target molecule. Now in the next system is, now in the last target molecule, we can see that we have introduced the nitro group at the end, because these were mostly very much deactivating and hence they were introduced at the end. The next guideline is, if the functional group interconversion is needed during the synthesis, it may well alter the directing effect of the group. Therefore, other substituents may be added either before or after the functional group interconversion. So obviously there would be sometimes we require functional group interconversion. Now in this system, if I want to have a orthopara directing system, there will be a methyl. If there is a carboxylic system, then it is a meta directing system. Orthopara directing methyl, I will have a CCl3, CF3, which are again meta directing. Now meta directing NO2, again I can have NH2, which is orthopara directing. Now let us come to this kind of target molecule. We can see that there is a trichloro system and the chlorine system. First what we will be doing is, we will be trying to remove this 3Cl3. So instead of this Cl3, we will be introducing a CH3. This will be done by functional group interconversion. Further, this Cl is disconnected, so that now only what I am having is the toluene system. In the synthesis, we can see that the toluene system reacts with Cl2 in the presence of FeCl3. What will happen is a chlorine is introduced. This is with respect to the para position. Now this chlorine gets introduced later when I react it with Cl2 in the presence of PCl5. I can easily introduce, in place of these 3 protons, I can introduce the Cl3. That is CCl3 could be introduced. If I want to replace this CCl3 also, in the presence of antimony pentafluoride, I can do again a functional group interconversion. Instead of Cl3, I will be now having a F3 system. So either before the addition of the functional group interconversion or after, I can introduce certain groups. Next condition is, many groups can be introduced by nucleophilic substitution on a disonium salt made from amines. At amine stage may be advisable as the amino group is strongly orthopara directing. We always know that NH2 group is a orthopara directing group. So this is going to now help in terms of the formation of a disonium salt. Now this disonium salt, if there is a presence of disonium salt, various other groups could be introduced, and with the help of which we can achieve our target molecule. Now let us come to this target molecule. Now this target molecule has got a carboxylic system, it has got a Cl, and there is a biphenyl system. In the presence of functional group interconversion, carboxylic group could be now converted through CN. That is, CN can easily give me carboxylic group upon hydrolysis. So this is my functional group interconversion. Now diazotization and nucleophilic substitution. So what we can do, this CN can be further converted to NH2 by the help of a diazotization system. The CN gets converted to NH2. Next is the Cl can be removed by CCl chlorination. We can further introduce this by the chlorination system. So what remains is just the NH2. Further, I can do a functional group interconversion upon reduction. That is, NH2 can be converted to NO2. NO2 can be reduced to NH2. Again, I can do a CN nitration. Nitro group can be easily introduced by the nitration system. So this NO2 also can be disconnected. Lastly, I will be getting a biphenyl system. Lastly, I will be getting this biphenyl system. So in this particular retrosynthetic analysis, first carboxylic group is converted to CN, then CN is converted to NH2 by the diazotization. Cl is removed because we can do a further chlorination. NH2 can be converted to NO2 because NO2 can be reduced to NH2. Further, CN can be removed because we can easily introduce the nitro group by the nitration system. What remains with us will be the biphenyl system. So in the synthesis, biphenyl system reacts with HNO3 and H2SO4 to give me a mononitration. This is because biphenyl systems are not planar system. They always remain in two different planes, and hence only mononitration can be done. Now after the mononitration, in the presence of hydrogen and palladium catalyst, NO2 can be converted to NH2. That is again protected by acetic anhydride. So we will be getting an NHAC. This in the presence of Cl2 and HCl and hydrolytic system. With respect to the NHAC system, there will be a Cl which gets introduced. Now this hydrolysis system, it is also going to remove the AC, that is your protecting system of the acetic anhydride, that is the acetyl system can be removed by the presence of the hydrolytic system, and in turn there is a Cl which gets introduced ortho to NH2. Further, on diazotization in the presence of HCl and copper cyanide, NH2 gets converted to CN. This CN upon base hydrolysis gets converted to the carboxylic system, which is my target molecule which I wanted to synthesize. So for the next guideline, for introducing two orthopara directing groups meta to each other, a dummy amino group is introduced, and it is after setting up to required orientation, it is removed by diazotization and reduction. Now, if there are any electron donating system, definitely if there is an electron donating system, they are always ortho and para direction. But if I want to introduce two ortho para directing system meta to each other, then what we will be doing is we will be first adding an NO2 group, so that there will be a dummy introduction of an amino group. Further, I can introduce the meta system. Let us see this. Now, there is a benzene which is substituted R. Para to this position, I am going to introduce a NO2. Now, R is an electron donating system. If I want to introduce anything with respect to R at the meta position, I should block my para position. So, how did I block my para position? By the introduction of NO2. NO2 can be further reduced to NH2. Now, further if I want to add this X, this will be electron donating system, and NH2 is also electron donating system. They are both orthopara directing, but then because the para systems are already occupied, what we can do with respect to R, we can easily introduce this X to the meta systems, so that with respect to this electron donating system, another electron donating system like X can be easily introduced. Further, what we can do is, in the presence of NaNO2, HCl and H3PO2 or ethanol, and in the presence of protonic environment, I can easily remove this NH2 and meta with respect to the electron donating system, another electron donating system can be easily introduced. So, with respect to that particular guideline, this is the target molecule. Now in this target molecule, I can see there is a carboxylic group, there is an OH and there is an NH2. Now first I will be doing a functional group interconversion. So this NH2 is getting converted to NO2. Next we will be introducing an dummy amino group, where I will be introducing this dummy amino group, that is para with respect to OH and meta with respect to the carboxylic system. Further, I will be removing the CN nitration, that is I can easily remove the NO2 group because I can do a nitration system. And then upon again functional group interconversion, I can remove this NH2 to NO2, that is NH2 is converted to NO2. Further, upon nitration, I will be getting an orthohydroxybenzoic acid. So this will be my starting material. So synthesis of this particular target molecule goes like this. There is a substituted OR system, that is OH is now converted to some OR, that is electron donating system only it is some substituted carboxylic acid, that is benzoic acid system. In the presence of HNO3 and H2SO4, I'll be doing a nitration. Now carboxylic system is a meta-directing system, it will go to a meta direction, and this is a para-directing system, it will definitely go to a para-directing system. Further, in the presence of hydrogen and palladium catalyst, in the presence of acetic anhydride, NO2 gets converted to NH2 and then it is protected by AC. In the presence of HNO3, OH and hydroxyl, in the presence of hydroxyl group and water hydrolytic condition, another nitration is introduced, another nitro group gets introduced, and in turn this AC, which was a protecting group, is also removed. In the presence of HNO3, that is diazotization, in the presence of ethanol and protonic environment, NH2 is getting removed now. So the dummy that we had introduced, now it is getting removed. Now further reduction in the presence of iron hydroxide, we can either reduce this NO2 to NH2. What we are doing is we are reducing the NO2 to NH2. Now finally, after deprotection, this OR can be removed and we'll be getting an OH. That is, my target molecule could be synthesized. So what we have done in this particular synthesis is we have introduced a dummy NO2 system first, and then I have converted that dummy into NH2. Later in the process of the reaction, we have removed that dummy so that two electron donating system were introduced meta with respect to each other. If you want to introduce two electron donating system meta with respect to each other, so this is the way we have to do. We have to introduce a dummy system first and then we have to go on doing the reaction. The next is, look for the substituents which are difficult to introduce. It is often good strategy not to disconnect them but to use a starting material containing such a substituent. Now, for example, if I want a presence of OH, I want a presence of OR, generally we do not go and disconnect them. What we do is we take them as a starting material and go on doing the reaction. The next point is, look for the combination of substituents present in the target molecule and in readily available starting material, particularly if it would be a difficult combination to introduce. Now, for example, orthohydroxybenzoic acid, orthohydroxybenzaldehyde, there is a diol system and there are various substituted xylenol systems. There will be certain biphenyl system, there will be orthoaminobenzoic acid, such systems which cannot be synthesized easily, like for example orthohydroxybenzoic acid or your salicylaldehyde system or your system like biphenyl system. Such systems could not be easily synthesized. So what we can do is we can choose them as the starting material only without even doing a disconnection. We will be choosing them as the starting material and further will be continuing for the reaction. So this is one of the guidelines. The next guideline is, avoid sequences which may lead to unwanted reaction at other sites in the molecule. Now, for example, there would be many other byproducts which may be synthesized. For example, benzaldehyde, when it is reacted with HNO3, we will be first of all getting a metanitro group, that is metanitrobenzaldehyde. This is 50%. Now this is my target molecule which I want to synthesize. But HNO3 is also an oxidizing agent. Instead of stopping at an aldehydic system, it will be further continued to an carboxylic system. So such system should be avoided. To overcome this, what we have to do, instead of picking up benzaldehyde, we will be picking up benzoic acid only. So benzoic acid upon HNO3, what will happen is NO2 group is introduced at the meta position. So what we will be getting is metanitrobenzoic acid. Further, in the presence of lithium aluminium hydride, there is a reduction of this carboxylic group to give me an aldehydic system. So in this way, I can end up getting my target molecule in a 100% yield, whereas here I would be getting it in a 50% yield. So such things should be avoided. Lastly, the freeze rearrangement, Remer-Timers reaction are the two reactions which can give equally large amount of ortho products. So this can be used to introduce ortho substituents with other substituents present, but one OH group is needed in the molecule. So what we will be doing is, if we want to introduce anything in an ortho system, we will be choosing a freeze rearrangement and Remer-Timer reactions.